This is the Digging Deeper for Climate Change Activity 2 paleoclimates. A paleoclimate is a climate that existed sometime in the past. It may have been a few centuries ago, or it may have been many millions of years ago. The Mesozoic era, which was from 245 to 65 million years ago, had a much warmer global climate than today. In the image on the right, you can see from the late Jurassic period, 145 million years ago, Dinosaur National Monument in northwestern Colorado. In the Jurassic period, it was a warm, wet grassland. Currently, it is desert and canyons. Very different climate than it was then. Later in Earth history, during the Pleistocene epoch, 1.6 million to 10,000 years ago, large portions of North America were covered by glaciers, the map of the extent of which you can see on E103 in the EarthCom book. The climate was colder and drier, with repeated ice ages and interglacial periods. The last ice age retreated about 10,000 years ago. In Colorado, this map on the left-hand side of your screen here, the blue areas show the portions of Colorado that were glaciated. We were not covered by the continental glacier. In eastern Colorado, the darker brown you can see are sand dunes. Written weather records only go back several hundred years, many places as late as the 14th century. Some parts of China have weather records back to 2,000 years ago. Most of these weather records are anecdotal. They're just stories people said whether it was cold or hot, wet or dry. Systematic records with actual technical measurements only go back about 200 years. Galileo invented the first thermometer in the late 16th century. An accurate anemometer, or wind meter, as shown here, dates back to about the 1800s. This digital weather station is a very recent phenomenon, and having systems of them around the world to accurately record data and be able to match it up to show what the world's climate is like at any time is a very recent phenomena in the last 50 years. Therefore, paleoclimatologists must use climate proxies. These are artifacts which stand in for weather data. One of these proxies is fossil pollen, which will blow in the wind or be carried into a lake or pond by water, either rainfall or in a stream, and then it will settle into the sediments, and the sediments layer upon layer will build up in the bottom of this body of water, and the lower down in the sediments the pollen is found, the older it is. The types of pollen will tell the scientists what kind of climate was around that body of water at the time that the pollen landed there, because certain plants will only live in certain climates. Another climate proxy is ice cores, taken from Greenland and Antarctica. These continental ice shelves, continental glaciers, are the only two left in the world. The ice core is taken by drilling out a very long tube out of the center of the glacier. Then they pull it out, lay it down, and look at the different layers in the core. In the image at the top of the screen, you may notice a dark band partway up the ice core. This is a heavy layer of dust that was trapped in the ice. When the weather is colder and drier, the winds are more likely to pick up dust from other parts of the world and blow it into the air, and it will land on the ice shelves and get buried by subsequent snowfalls. Since there's a heavy layer of dust here, we can predict that at that time it was cold, it was dry, and windy. The ice also includes isotopes. When the snow falls, it's made of water, and water is composed of oxygen and hydrogen. When the world's climate is warmer, the oxygen isotope 18, which is slightly heavier than the normal oxygen isotope of 16, has a greater proportion of the oxygen in the atmosphere. Therefore, the ice and water that form at that time will have a greater proportion of oxygen 18 in it. When the climate cools, the oxygen 18 ratio will decrease. Also, the falling snow will trap air bubbles from the atmosphere at that time. So when scientists analyze the air bubbles, they can say that there was so much methane in the air at the time, so much carbon dioxide in the air at that time, and then they can say that the climate was warmer or cooler based also on that additional evidence. Glaciers, which form in the mountains from accumulated snowfall, act very much like the continental glaciers that covered much of North America. What the glaciers do is they will carve their own valley because of the immense mass of the ice accumulated. While they're doing so, they grind up and tear off pieces of rock. The further they go, the smaller those pieces get, and they push that rock along ahead of them, or as evidence here, we have this medial moraine, they carry it along inside the glacier. If the glacier gets to the ocean, it can break off and form an iceberg. The iceberg will carry with it any debris that was in the medial moraine. As the iceberg floats out to sea, it will begin to melt, and any sediment contained within it, because of the medial moraines, will then settle down to the sea floor. The sea floor sediment, because it is constantly moved and ground against each other by the water of the ocean, will have a much finer quality than the coarser sediment from the iceberg. Terminal moraines, such as is shown on this map of Ohio, show the extent of glacial coverage from the continental glaciers. This is sediment that was pushed forward by the glacier and then left behind as the glacier retreated. And we can see that there were several periods of glaciation where the glaciers advanced and retreated and advanced and retreated. So we know over time, by dating these moraines, when the glaciation periods occurred. When the glaciers retreat, they often leave behind a very fine powdery sediment that blows around when the winds pick up. When this is deposited, it's called loess. There are large deposits of loess in the central United States where the glaciers covered large portions of the continent. Another climate proxy that scientists use are trees. Tree ring data tells us how the climate was at the time of the tree's life. Thicker rings means it was a very well-watered, healthy tree and it was growing quickly. Thinner rings meant the tree was struggling more to keep up with growing. Unfortunately, very few trees live long enough to record significant portions of history. Two exceptions are the giant sequoia. In the upper left picture, there is a small version. The sequoia can live 500 to 3,500 years, can be up to 50 meters tall, and 6 or more meters wide. In the bottom right picture is a bristlecone pine. This is a species that doesn't grow very large. It actually grows very, very slowly and can live from 3,000 to more than 5,000 years. So when we find a deceased member of these species or take a non-invasive sample, we can estimate how the weather was at this particular location where this tree is growing, and then extrapolate that to the regional climate of the time, matching that with other data that we may have to estimate the global climate of that time.